we have obtained the solutions for a uniformly moving charge and also for a charge accelerating at non-relativistic speed. That was Thomson's argument. We now obtain the general solution for the potentials and fields that arise from time varying sources, that is charge and currents that are varying with time. To understand how these solutions evolve, I will take you back to our basic lectures on waves. So, let us begin. The topic of this lecture is solution of the wave equation for scalar and vector potential for charge and current densities. Changing with time. And this will give retarded solutions, which we will see in a minute what it means. So, as I said, if you go back to our lectures on waves, one particular example I had taken there was a long string starting from x equals 0, and this end was being shaken up and down in a periodic manner. So, that the displacement was given as y t equals some amplitude sine of omega t. Then, if you want to find y x t, we wrote this as y of x equals 0 at time t prime equals t minus x over v. So, the solution becomes a sine omega t minus omega over v x, which we write as a sine of omega t minus k x, where k is omega over v, known as the wave vector. In general, I can have at x equals 0 a general time dependence y t. It could be any other function rather than being harmonic, and then the solution at y x t would be equal to y at 0 at time t prime equals t minus x over v, which will become then y t minus x over v. This time is known as retarded time, and what it says is that at point x, the displacement is the same at time t as it was at point x equals 0 at time t minus x over v, or at retarded time. Now, for ease of mathematics, we are going to use complex notation. So that the time dependence, harmonic time dependence, is given as e raised to minus I omega t. And in this, the solution would be written as, for harmonic wave y x t equals e raised to I k x minus omega t. times an amplitude, which could be complex number. So, this is a general background. So, what we learned from this is that a displacement given at a point propagates with the speed v in a non-dispersive manner, then y x t is given as y at x equals 0 and at time t minus x over v. And in the complex notation, therefore, y x t is amplitude, which could be complex, e raised to I k x minus omega t. Now, I could have obtained this space dependent part by solving what is known as Helmholtz equation. I am introducing all these terms, which will be handy as we progress. So, the wave equation that we are solving is d 2 y over d x square minus 1 over v square d 2 y over d t square equals 0, and I am taking y x t to be equal to some y x e raised to minus I omega t. When you substitute this in the wave equation, you get d 2 y over d x square minus 1 over v square d 2 y over d t square as d 2 y x over d x square plus k square y equals 0, where k is omega over v, and the solutions for these are y x equals e raised to plus or minus I k x. If I take the plus part, it is a wave traveling to the right, and if I take the minus part, then it is a wave traveling to the left. So, this is one dimensional wave which propagates and how we get the solution. Let us look in 3 dimensions. For 3 dimensions, I cannot think of a string, but what I am going to do is, suppose I have a sound source in space at some point. Here is the sound source, and it is giving out sound waves, which are traveling all around in an isotropic manner. The sound waves are pressure waves. So, let us say at r equals 0, the pressure P varies with time as P 0 e raised to minus I omega t. Then, since the waves are going to travel isotropically all around, I may expect that P r t would be proportional to e raised to I k r minus omega t. With a slight difference compared to one dimensional case, here the amplitude could be r dependent. This is because as the pressure wave goes out, the energy gets distributed over a larger and larger area. So, amplitude may go down. So, we will allow for that possibility and write P r and t as some function r e raised to I k r minus omega t. And going to substitute this in the 3-dimensional wave equation, which is Laplacian of p r t minus 1 over v square d 2 p over d t square equals 0. Del square in spherical coordinates is 1 over r square partial r square partial r again, and dt square is very easy to take. You do this, and finally, once you manipulate all the terms, the equation you get is 2 over r f prime plus f double prime plus 2 I k f prime plus 1 over r f equals 0. That is the equation for f. Let us solve this. Just to recap, I have this source of sound which is giving out sound waves isotropically, and we are taking p r t to be equal to a function of r, only r, e raised to I k r minus omega t. This is a function of r only because everything is isotropic, and when I substitute this in the wave equation, del square p minus 1 over v square d 2 p over d t square equals 0, I get the equation for f, which is 2 over r f prime plus f double prime plus 2 I k f prime plus 1 over r f equals 0. The real and imaginary parts both are going to be independently 0, and therefore, I get f r equals 1 over r. It satisfies both the equations. The real part is 0 and the imaginary part is 0. Therefore, I can easily write that the pressure r and t goes as some constant over r e raised to I k r minus omega t. So, this is known as the spherical wave. So, as the wave goes farther out, the amplitude decreases as 1 over r. Now, let me write this solution in a slightly different form, which will be used later. So, go to one dimension again. Let us say this string was not at x equals 0, but at x equals some x prime, and it is being shaken up and down as y t. Then the solution y x t will be equal to y at x equals x prime at time t minus x prime over v. So, I can write this as y t minus x prime over v. Again, notice that this time is that retarded time. So, what we have considered is this string which is being shaken up and down at x equals x prime with y t, then the solution y x t is equal to y of t minus x prime over v. I can also write this as equal to, and now I am developing a form which I will be using later, integration of y t prime delta function of t prime minus t minus x prime over v dt prime. So, this contributes only at t prime equals t minus x over v. But this is a way of writing it. In addition, suppose I had this displacement coming not only from one place, but suppose there is this string and I am shaking it up and down here at different x primes, and from everywhere from this length dx prime there is a displacement, let us say y prime y tilde x prime dx prime. So, here is the string which is being shaken up and down at different places, and let us say all these places are to the left of where I am going to observe things. So, x is way out of it, and from everywhere I am getting a contribution y tilde x prime dx prime from that string of length dx prime. Then the solution at x is going to be a superposition of displacements arriving from different places, and that is going to be y x t equals I am getting y x prime at time t prime delta t prime minus t minus x prime over v. This is tilde dx prime dt prime integral. Notice that retarded time is different for different x primes. So, these waves start from different x primes at different times and arrive at the position x at the same time, and they get superimposed. So, this is the form I am going to write it in. Of course, if you take y to be harmonically varying, you get your previous solution back. In the same manner, I can do for 3-dimensional waves. So, suppose in this space I had different sources, one source here, one source here, one source here at different r primes. And I am getting a pressure P tilde r prime from the volume around that r prime, and this is varying with time. So, what I am getting from different points is P tilde r prime t prime d tau prime. D tau prime is that volume element. Then P at R t is going to be a superposition of all these, and I can write this as integral P tilde r prime t prime delta function of t prime minus t minus mod r minus r prime over v d tau prime dt prime. So, what is happening is that I am picking up information at time t prime, which is the retarded time for a given position r, and all these pressures are arriving at point r at the same time, and they are being superposed. I can superpose them because the basic equation is linear. So, we have understood how these waves are formed, how they arrive at a certain point, and what their amplitude at that point is. So, now we are ready to go to electromagnetic wave. I will first do fields, show that they become complicated, and then go to potentials. Argue it like this and then show you mathematically that this indeed is the solution. Recall now, if I have a charge density rho r t and a current density J R T, the equation that we had derived a few lectures back for the electric field was Laplacian of E minus 1 over c square d 2 E dt square is equal to mu 0 d j dt R t plus gradient of rho R t over epsilon 0. So, if I consider a small volume d tau prime, this gives a solution for E at r, but that will be considered a retarded time. So, d tau prime, the solution would be 1 over 4 pi times all this term mu 0 d j over d t prime r prime t prime plus gradient of rho r prime t prime over epsilon 0 1 over r minus r prime. This would be the contribution of this at time t prime, and this has to be retarded if I want to calculate the field at r at time t. So, this is going to be multiplied by delta function of t prime minus t minus r prime over c and integrate over t prime. Integrate this and you get your answer for E. I did exactly what we were doing for these pressure waves and everything. I wrote that formula in the form that I can take easily to this part. So, form a volume at r prime, there is this source that gives out a solution, but that solution has to be considered at a retarded time, and therefore, I multiply by the delta function. So, let us now write it cleanly. For this source, E will be equal to 1 over 4 pi comes out. It should be with a minus sign, remember, because in my Laplace's equation there is this minus sign, and this delta function arises because of this wave part. So, this is going to be minus 1 over 4 pi integration d t prime d tau prime delta of t prime minus t minus r prime over c multiplied by the source term, which is then mu 0 d j over d t prime at r prime t prime plus grad of rho r prime t prime over epsilon 0, and on outside there is this 1 over r minus r prime. That is the answer. Notice that if the propagation was instantaneous, right, So, if C was infinity, which is called as action at a distance, then my solution at R would have been E R t is equal to minus 1 over 4 pi integration of, because the second term in the wave equation does not exist, it is just the solution of the Laplace equation. So, it would have been integration of d tau prime. There will be no delta function over r minus r prime, just like the potential of the source term, times mu 0 d j over d t r prime t plus grad of rho r prime, this is a prime with a prime sign, t over epsilon 0. That is it. That would have been the answer, because everything is propagating instantaneously. However, because the speed of light is finite, you get this retardation term here. Delta t minus t prime minus t minus r prime over c. I'll just give you some notation. The solution E R t, which is equal to minus 1 over 4 pi integration d tau prime, that is integration over the volume, all that source term divided by r minus r prime. Generally, one shows it like this, retarded. What it means is, when I write a function f r prime t prime retarded, it means this is equal to f r prime t minus r prime over c. This is what we are doing when we are writing our equations. In the same manner, for magnetic field, I have the equation del square B minus 1 over c square d 2 b over d t square is equal to minus mu 0 curl of j. So, I can write B equals B at position r time t equals mu 0 over 4 pi integration d tau prime curl prime of j r prime t prime. Let me write this retarded over r minus r prime. So, we have gotten the terms for E and B both, and they involve derivatives of charge density, derivatives of current density, and so on. These, by the way, when expanded, are known as Jeffimenko's solutions, and they are like Biot-Savart or Coulomb's law like solutions for electric field and magnetic field directly. However, we do not want to get into all this complicated source terms. So, it is easier to formulate things in terms of potentials. So, we are going to focus now on wave equation for scalar and vector potentials. And to keep symmetry, I am going to work in Lorentz gauge. Recall that in this equation for the vector potential is del square A minus 1 over c square d 2 A by d t square equals minus mu naught j r t, and del square phi minus 1 over c square d 2 phi over dt square equals minus rho r t over epsilon 0. Again, now with this background that I just gave you, I can write the solutions for these directly. I can write that A at r at time t should be equal to, if c were infinity, this would have been the integral of the potential type that we have been looking at, but now the minus sign goes away. It will be mu naught over 4 pi integration d tau prime j r prime t prime, and I can write retarded divided by r minus r prime. And similarly, I can write phi r t equals 1 over 4 pi epsilon 0 integration d tau prime rho r prime t prime retarded over r minus r prime. Let me write these terms in very explicit manner next, so that we understand the meaning of it. So, given this source rho r t and j r t, the solution of the wave equations for the vector and scalar potential is A r t equals mu 0 over 4 pi integration d tau prime j at r prime at time t minus mod r minus r prime over c divided by r minus r prime. And phi r t is going to be 1 over 4 pi epsilon 0 integration of d tau prime rho r prime t minus mod r minus r prime over c over r minus r prime. So, whatever potential I am observing at a certain point starts from a source at a distance r prime and takes some time to reach the point where I am observing it. Time taken is modulus r minus r prime over c. And now one can superpose the solutions coming from all these places and get the final answer. Pictorially, here is the origin and my coordinate system. I have these sources somewhere, and if I am observing the potential at r, then all these sources are giving out these potentials, which start at some time t prime, which is t minus r prime over c, reach here, and they are all superposed and lead to the solutions that we have written. These are known as retarded potentials. And then you can calculate from this the E field, which is minus grad phi minus dA dt, and the B field, which is curl of A, which we will be doing in coming lectures. So, let me conclude this lecture by stating that we looked at the waves propagating in a non-dispersive medium and wrote the general solution in a form that can be interpreted easily. And taking a hint from there, we wrote the solutions for the vector and scalar potentials arising from time varying charge densities and current densities. Thank you.